Assalamualaikum and good day everyone. So today's videos we're gonna continue with our topics, new topics, lead lag controller design. So we gonna go through the lead controller first. Lead controller has a similar effect as the PD controller, which is to improve the transient response. PD controller can be viewed as the ideal lead controller, and however PD cannot be implemented using op-amp, the lead controller is a good approximation to PD controller. So this statement says that in order to have a PD controller, we need to use op-amps. Okay, so when we develop the PD controller using op-amps, we will have the controller that have the transfer function of KC as plus A. However, if we do not have op-amps, for example, we have limited resources, we can use normal circuitry to get a lead controller that is, we can use it as a good approximation to the PD controller. And for the lead controller, we have the transfer function for the controller is GC equals to KC S plus A S plus B. So remember that for the PD controller, we have a GC for the PD controller is KC S plus A. So here we have additional S plus B in the transfer function. So the value of A is greater than 0 but less than B. Okay, for the PD controller, the PD0 will be used to reshape to speed up the response, which is the root locus, to achieve the desired transient response. And in this case, the pole of lead controller, which is B here, will influence a bit of the locus shaped by 0. So in order to minimize the effect of pole, we should put the pole of B large enough, okay, so that it will imitate the controller, the PD controller using the op-amp. Okay. Next, we consider the following plan. Again, say we have GP equals to 10 over S plus 1, and then the design specification is percent overshoot, which is less than 10%, and we also want the peak time for the response equals to 1 second. And the design procedure for the lead controller are similar to the previous examples. We need to choose the desired closed loop poles, and from the previous example we have calculated that S equals to -3 plus minus J3, so to get a TP around 1 second. As you can remember, the formula is something like this. So we have decided our TP is 1 second, so we decide the frequency, the omega D equals to 3. So we just arbitrarily put at the real value equals to -3. All right, and then we want to have about 5% overshoot, which is equals to zeta 1 over square root of 2, or 0.707. Okay, however, we expect both of these initial targets will be degraded after introducing 0 and pole of lead controller to the system. So what we desired and what we set here is just an initial point, so that we have a starting point to fine-tune later on. Okay, at S equals to -3 plus minus J3, we select A equals to 1 to cancel the largest pole of the plant, right? So we select we have GC equals to S plus A and S plus B, and also we have KC here. So we select A equals to 1 so that we have 1, and then we can cancel the pole of the GP to the 0 of GC. Okay, so we know that the root locus, the point on the root locus will result in a negative 180 degree of angle. So we can calculate the unknown angle here. So in this case, we select A, and A equals to negative 1, which is we can cancel out this one and this one. What's left only beta and theta 1 here. So we can now proceed with the calculation to get the angle of beta, which is here negative beta minus angle of S. So basically beta and S is pole. Beta and S are poles. So the summation of 0 minus summation of poles. So negative. That's why you have here negative term here, right? So when we rearrange, then we can get something like this: 180 degree minus the angle of S, and then we calculate the angle of S to be 135 degree, and then the summation, the resultant 180 minus 135 degree equals to 45. From the 45 degree, we can calculate the angle of, the value of B. Okay, so we have beta here, so we can use the tangent here, which is 3 over 3 here. Okay, so this is 3, this is 3. Alright, we can take the absolute value. Okay, so the result of this equation equals to 6. Okay, so now we have our GC equals to KC S plus 1 S plus 6. Alright, so what we don't know now here is only KC. So we can calculate the value of KC from the formula here, which is we have GC multiply with GP, okay, and then we take okay, so it is just KC equals to 1, okay, so which is KC equals to 1 over GC GP. Okay, that's why we get S plus 6 and S, and then we have S, here S equals to negative 3 plus J3. Okay, so from the calculation we have KC equals to 1.8, and we can put it into the KC of our controller. So we have this term. Okay, so now we insert into the compensator, into the Matlab, and then we will get something like this. And then we have this one, the response. So let's go to the Matlab and do, okay, here. All right. So our GP here is we use a ZPK. So we have something like this. We have ZPK of GP 10 over S plus 1, and then we decided to have S and equals to negative 3 plus 3i, and then we have our A is equals to 1. And then we can find the angle in radian here is pi minus angle of S. Okay. Okay, let's look at this. So we have here is 180 is pi minus the angle of s here, and then we can convert it into degree. So we have this one, and then we can use a rad to degree to convert it, and then what we get is 45 degree, and then we can use this formula. So we have b equals to 3 plus 3 over tangent 45, which in this case we take the absolute value of the real of the imaginary s here, real of s component, and we take the absolute value of imaginary of s here over tangent in degree tan d of angle beta here, and then what we get is b is equals to 6. Okay, this is actually the initial our s plus 1, s plus 6 without the kc, so we assume kc is equals to 1, right? And then we can multiply gp, which is our plan, with the initial gc that we set, and then the mean real here is actually you can type help mean real. Okay, for this one the function is actually produced for a given LTI model system and equivalent model MCs where all cancelling pole zero pairs or non-minimal state dynamics are eliminated. So in this case, remember that we have s plus 1 for the plan, the pole at s plus 1, and for the GC, let me remind you. So our GP is 10 over s plus 1, and then our initial GC here is actually s plus 1 over s plus 6. So we can use, if I multiply both GP and init GC here, what we have is 10 s plus 1 over s plus 1, s plus 6. So I don't want the s plus 1 term here because we can cancel out each other. So I use the function mean real. So let's say I use g equals to mean real GP multiplied by init GC. So we have 10 over s plus 6. Okay, so we have a g here. So g is actually a ZPK. So if you double click on g here, what you have is we have this property of ZPK here. So we have ZPK. So we can call g dot p here. So g dot p is actually an cell array. Okay, cell array. So you can call something like this 1 1 because it is 1 by 1 cell array. Cell array is called by using the curly bracket. So g dot p curly bracket 1 by 1, you have this 0 and negative 6. Okay, which is correct because in our case g here is 0 and negative 6. Okay, so when we call each of the element of GP here, we can call by using this term g dot p curly bracket 1 1, and then we have parenthesis, we have bracket here 1 1. So we call this function, we get 0. So if we call 2 1, which is row number 2, we have negative 6. Okay, so that is why for this okay, we calculate Kc here is s plus 6 s over 10. So I can call using this formula here, so which is absolute value of s minus g dot p. Why I use minus here? Because the GP here is actually roots. This is a roots, s plus 6. So the root of s is -6, so I want to have s plus 6 here, so that's why I put s minus GP here. So it actually result in s plus 6. Okay, and similarly to this one, it is actually s so this one is 0 actually. S minus 0 is actually equals to s. And this one is s minus 6 equals to s plus 6. And then I call gk. So what is actually gk? Gk is the value of this. Okay, we have the k. Our k is 10. So I call the g dot k equals to 10. So we can run this, we will get our Kc equals to 1.8. And then we can put together the Gc is, we have ZPK negative A, P is negative B, and we have our Kc equals 1.8 here. So we have this term, right? So this term is actually what we found earlier in our lecture notes. Here is 1.8 s plus 1 over s plus 6 here. Okay, and then we can call the initial CISO. So I call this function. So I set the G value equals to GP, C value equals to GC, and we can call the CISO tools here. So I run everything and I get this. Okay. So this actually will result in peak amplitude of 1.04 and overshoot of 4.32. So the question asking about the percent overshoot is less than 10%. So let's say we want to have close to 10% here. Actually, we can get 10%. You see here our time is 1.04, so which is close to the design requirement. So for this one, let's say we increase to 0.4, for example, and what we get here is actually, yes, we get 8.77 percent overshoot. So maybe I try to increase a little bit. Wow. Oh, okay. So this one we get, maybe I can increase to 0.405, for example. For one, so we get here the overshoot is close to 10%, which in this case is 9.2%, and then at time 0.798, which is we have successfully obtained for both overshoot requirement and peak time requirement. Okay, I think that's it for this examples. Next, we will see about the lag controller. All right, thank you very much. See you in the next video.